Okay, then we believe it's working, and I start. I call this research perspectives on biofuels. It's a small and selective approach because there's no chance of looking at the whole field within the framework of this presentation. Biofuels have gotten a bad reputation in some contexts. Here is a joke saying that your child is hungry, my sieve is ravenous. So it can be controversial, and there's enough truth in it so that it's something that we need to be careful about. And that is why, basically, for more than the last decade, the focus of biofuels research has been on finding sustainable ways of producing biofuels. So it's the research, as I encounter it as a chemist especially, but also in the wider interdisciplinary contexts, is that one is looking at sustainable feedstocks, new types of biofuels. For a chemist, that's great fun because there are such a lot of molecules that could be used as a fuel in an internal combustion engine. There's more efficient conversion routes, which also is fun for chemists. Improving the product quality and reducing the production costs. And the last bits of this is more like engineering, and I hope that somebody gets inspired to work more in that end too. Where does bioenergy come from? Basically, it comes from sunlight. The photosynthesis fixes carbon from the atmosphere as organic matter. And it needs energy to do it, and the energy comes from the sunlight. So plants are natural photovoltaic units, and they manage this all on their own. So it's a very simple way of collecting sunlight energy. How much biomass is produced? Well, I suggest you go into the reference if you want to really look at the numbers, but the primary production is large. Now I lost the terms, but anyhow, the natural primary production is somewhat smaller than the overall, and the human part of it that we use covers sort of half of it again already. And this means that we can't say that we have an enormous resource of biomass just waiting to be used. Like we heard in the first lecture, there are alternative ways of thinking about how to use what we have. And anyhow, it isn't in the same range as the petroleum resources that we now, in the course of a few decades, are producing from the North Sea. On the other hand, this is renewable, and if we find a sensible way of using it, we can continue to use it at the same level for indefinitely. So what the focus is on the feedstocks is to try to find the right feedstocks in terms of residues and wastes. Things that already are harvested, like things that won't be growing anymore anyhow, and where we are not using the residues in an optimal way. Agriculture has a lot of residues. Forestry has a lot of residues. We have the municipal wastes, whatever gets collected in your waste containers. We have things like sewage sludge, which has periodically gotten quite a lot of research interest because it's an obvious total gain feedstock if we can make something sensible out of it. For the types of feedstocks that aren't wastes, we have the possibility of growing energy crops on lands that wouldn't be used for food production anyhow. This could be, well, on land, but also it could be in water or in the sea in terms of algae, seaweed, etc., or microalgae that we can efficiently convert into energy products. And the efficiency of this is a very important factor for any kind of research approach into new biofuels. One example of this kind of approach is that we recently opened a pilot for microalgae growing at Mongstad, where they use CO2 from the refinery and heat from the refinery and produce microalgal biomass to extract the fats. Now, biofuels are not a high-value product. And again, as mentioned in the first speech today, the way to make it work would be to find some additional product that has a much higher value. And here one gets into the fatty acids that have good properties for humans. One can extract some part of the product and use the rest for biofuels. If we look at new biofuel types and more efficient conversion routes, there's an enormous range of possible approaches. And this is just an overview from a previous European project. I mean, one can do the direct combustion and recover the heat. For a chemist, that's not very interesting at all. Thermochemical transformations are ways of changing molecules into other shapes and properties, where we can take the biomass, which has a considerable level of oxygen, and we can do chemical conversion to give hydrocarbons in the ideal case, but also other liquid fuels, or we can go through the route of synthetic gas and Fischer-Tropsch type conversion and get pure hydrocarbons again. So the combination of the biomass resources and the choice of thermochemical conversion has a very wide range of potential applications, including hydrogen or methane if you want to drive a hydrogen car instead of a diesel car. But my main point here is that once one goes into this, basically all of these product types are interchangeable depending on what technology approach one chooses. Then we have the whole range of biotechnological solutions, which also are very suitable for some of the nastiest biomass types. One can produce methane from nearly any kind of wet waste, and the methane is chemically identical with the methane in natural gas and can be used in all the same ways. The only challenge there is to clean out the CO2, and there are good technologies for that. One can heat treat it with air to make it easier to compost. But the main pathway here for fuel use is to ferment any kind of fermentable biomass and make ethanol, which can be used directly in a gasoline engine. So for gasoline engines, it's ethanol, and for diesel engines, it's other types of conversion. Well, one has the biodiesel, the conventional biodiesel from oil, also as a way here. So there are lots of ways to go forward, and I did a quick check on the bibliographical search on publications last year saying biofuel, and you get 800 on biofuel and 250 more on biodiesel and so on. So there's lots of activity. And for an organic chemist, this is really interesting. So then I'll just zoom in a little bit at what we're doing. We are doing thermochemical conversion processes. And we have focused recently to a large degree on the biopolymer of lignin. I will define it for you in a moment. And we want to make biofuels and chemicals. We are also expanding this in a way by saying that we want to make catalysts that can convert our first level oil into aromatic hydrocarbons, which will be a generally applicable type of technology if we manage to make it work, and I'll talk a little bit about that too. So lignin is a third of the content of polymers in timber. If one wants to make paper or bioethanol, one wants to have the carbohydrates, the cellulose and hemicellulose, separated from the lignin. And there is good technology to use there. This is being done in Sweden in large scale at Sekab, for example. The lignin residue cannot be fermented, and this is why we chose to focus on it, because if we can get value-added products out of the lignin, the idea of the whole conversion route will be much more viable. And this can very well be combined with taking the good part of the wood and making planks and building materials, and taking the rest into our fuel production process. This is lignin. I promise you won't get many chemical formulas, but this is just to show that lignin is a polymer, that it's complicated, and it doesn't look like a fuel in itself. We heat it together with formic acid and a solvent, and we make small molecules. Depolymerization and further conversion into molecules with less oxygen. The conventional petroleum-based fuel has no oxygen, so the deoxygenation is an important part of this processing. However, if we look at value-added products, already at this level, we have guaiacol, which is an industrial bulk chemical that is being used in large quantities and that has a much higher price than the fuel price. So one should consider how much fuel we want to make and how much other chemicals we want to make. Our catalyst project really is looking at taking the monomers with one oxygen or two and getting them all the way to the hydrocarbon stage, which is comparable to what they would sell from Mongstad. The catalyst development is a very risky, forward-thinking way of making molecular models, synthesizing the catalysts, making them soluble in water and still active, and testing them again for this type of conversion. So this is ongoing research. The final points in my initial list was improving product quality and reducing production costs. This is not my field as an organic chemist, but I see that this is really the area where one needs the most work now, because a lot of academic research gives good results in the conversion, and then one needs to make a product that could be sold, and the academics don't know how to get on with it. And one should have academic industrial cooperation to get further on this, but instead we end up with being told that you must do more research before we can use money on it. Well, the Research Council says that, but you've gotten a lot of money for research, now you have to go and commercialize. So this is what's called the Valley of Death, and there's a lot of good biofuel projects that are there and don't know how to get on with it. So any suggestions on how to come further in that process will be very acceptable. What we in the field are looking at and would like to manage is to make a biorefinery. It's like an oil refinery, except that the input is biomass. One chooses the set of products that gives the best economical results, and one uses all the components of the feedstock that one can that are available. I mean, when we say that petroleum has such and such energy content, one really skips a bit that the petroleum goes through a very intense refining process that has been developed over 50 years at least, and we need to develop the biorefineries to a similar degree. We have one really advanced biorefinery in Norway, and that's Borregaard. They've stopped making paper a long time ago, and they make a very wide range of products from their wood feedstocks. We need to develop more of that kind of industry. So that was what I thought could fit in today.